All right, here we are. This is Monday, November 9th, 2020, AP Physics C, Mechanics, beginning of Chapter 6, Dynamics 1, Motion along a line. And in this chapter, it talks about Newton's laws, how they're used to solve problems, how dynamic problems are solved, equilibrium problems, mass and weight, models, frictions and drags, and how do we solve problems. Great. First, let's talk about the equilibrium model. Equilibrium means the sum of all the forces add up to zero. The sum of all the forces add up to zero. And in particular, we're saying the sum of all the forces in, let's say, the x-axis add up to zero independently, because motion in one direction is independent of motion in the perpendicular direction. The sum of all the forces in a y-axis would have to add up to zero. Truthfully, there is a third consideration that is at the moment theoretically beyond chapter 6, but I'm going to mention it today already, and it has to do with a concept called torque. After all, I have to have something that gives Costab something to fret about and worry. Well, gee, should I know that? Yes! Here, learn this. Torque is defined as a cross product, which I haven't taught you yet, between the axis of rotation of an object and the application of a force. R is the distance from the axis of rotation to the point of application of a force, of course. And cross product means it's the magnitude of that distance times the magnitude of that force times the sine of the angle between those two vectors. Yes, the sine of the angle between those two directions. So if they're going in the same direction, then it's 0 degrees. Sine of 0 degrees is 0, and there is no torque. The maximum torque would be when the sine of theta is equal to 1, which occurs at 90 degrees. So if I had a axis here and a rod here, and I apply a force there, and here's the distance from the axis rotation to the point of application of the force, of course. This direction is here, that direction is there, the angle is 90 degrees, and here we have maximum torque trying to make this thing twist about that axis rotation. That's torque. And in this problem, based on our math conventions, this would actually be a negative torque. Now, I mention that because equilibrium, to my mind, means not only do you see what I see? What is going on in this room? What is that? Children, I think you're right. Now I'm ticked off. And tick gone. Question is, where did it come from? The things that try to interfere with your education. All right, keep those funds coming to rebuild our schools. I was starting to say that when I think of the word equilibrium, to my mind, it means not only are the sum of all the forces equal to zero, but the sum of all the torques about any arbitrary axis are equal to zero. I will set this aside until we get to a later chapter, probably 10 or something, maybe 9. For now, consider this as an equilibrium example. I have a ceiling. I hang a sign from the ceiling. The sign of sort says, I heart physics. Yes, you probably have this over your bedroom. and I'm hanging the sign by two vertical strings. Boop, boop. And the sign has a mass of 10 kilograms. And the question is, so what is the tension in each one of these two strings? In this situation, they're both vertical. They're, let's say this is uniform density, uniform thickness, uniform shape, and therefore the center of gravity of the sign would be in the physical or geometrical center of the sign. If it has a mass of 10 kilograms, then the free body diagram would say, all right, its weight would be 98 newtons pointing down towards the center of the earth. The tension, well, what's going on? This sign does not move. It is in equilibrium. In this case, static equilibrium, meaning it's not accelerating, it's not changing direction or speed, which means not accelerating. Therefore, the sum of all the forces have to add up to zero. Therefore, the sum of all the forces horizontally have to cancel out. In this case, there are no horizontal forces and life is good. The sum of the forces vertically have to cancel out. Now, because the two strings are at the end point and the center of gravity of this thing is in the midpoint, the two tensions, you should have some common sense that says they're going to be equal in magnitude. And the two of them put together are going to equal the weight of the sign. So this is going to be a 49 Newton upward tension. And this one is also a 49 Newton upward tension. And ta-da, I have solved for the two tensions in this simple equilibrium example. What happens if I have that same sign and now I have the two chords holding it? I was really trying to draw them to suggest that they had the same angle, but that is not necessary. We'll do this one that says, yes, they're at the same angle. Let's say that they're making an angle of 30 degrees to the vertical, both of them, 30 degrees to the vertical. And it's the same sign. What happens to the tension? It's still an equilibrium problem. The sum of all the forces have to add up to zero. The sum of all the torques have to add up to zero. Something I think I would use as part of problem solving here. What's going on is that the tension now has to have two components to it. The vertical component is still 49 newtons for each one of these. 49 newtons. But in addition to holding up the sign, now each of these two ropes are in a tug of war with each other. The one on the left is trying to pull the sign to the left. The one on the right is trying to pull the sign to the right, and they are in a tug of war. They exactly cancel each other out. Geometrically speaking, though, the ratio of the lengths of the physical triangle here is identical to the ratio of the sides of the tension here. Meaning, this is a 30, 60, 90 right triangle where this vertical leg is 49 newtons. On a 30, 60, 90 right triangle, the hypotenuse would be length 2, the opposite leg would be length 1, and the adjacent leg would be square root of 3 over 2. Therefore, if I want to find the tension in this cable, let's see, square root of 3. Well, look, just divide it by the cosine of 30 degrees. So you're dividing it by 0.866. You're dividing it by square root of 3 over 2. You're multiplying it by 2, dividing by the square root of 3. You're powering up your calculator. Sorry, I don't have my calculator ready. Deploying calculator now. Deploying it. And my calculator says 49 divided by the cosine of, I'm sorry, I hit the wrong button. 49 divided by the cosine of 30 degrees is 56.6 newtons now. The tension has gone up, 56.6 newtons. And by symmetry in this problem, both ropes are now at 56.6 newtons. Anyone have any questions about how I figured that out? Brendan shakes his head saying no. Everyone gets it. It's just simple physics.
Cosine other than
Never mind, never mind. Yes, I used cosine. And I just realized I made another mistake in what I was doing. Oh boy. Okay, I resumed recording. Now, any questions? Do you guys have a double here? Of course they do. They are teenagers. Huh. That's a Canadian thing. Okay. Well, what happens if we do something that is not symmetrical? What if I have that same sign that, means you love physics? Got to write the sign. And this time, tension 1 is at a 60-degree angle, and tension 2 is at a 30-degree angle. Now, I'm sorry, you couldn't see what I'm doing. Now, the two tensions are not going to be the same value. But the sign still is not moving. Therefore, this is still an equilibrium problem. The trig slightly changes. I have a 60, 30, 90 right triangle on the left and a 30, 60, 90 right triangle on the right. But they still have to cancel in their tug of war. So the horizontal component of tension 1 pulling to the left must cancel the horizontal component of tension 2 pulling to the right. Elijah, you should be busy learning physics right now, not treating this like the morning show that you watch while you enjoy breakfast. So the horizontal component of tension 1 would be T1 cosine of 30 degrees. That has to cancel the horizontal component of tension 2, which is T2 sine of 30 degrees. If I were to, let's say, divide both sides by the cosine of 30 degrees, divide both sides, well, no, that's good enough. That says T1 is equal to T2 times the tangent of 30 degrees. I know you love math, and you probably recognize, kids, you can end your food discussions now during your 3-minute break. You can resume all that. You might recognize that you have two unknowns in this one equation, and it cannot be solved without a further constraint or piece of information. That second piece of information is that the two vertical components still have to hold up the sign. Therefore, oh man, how shall I put this? T1 times the sine of 30 degrees plus T2 times the cosine of 30 degrees still has to add up to 98 total newtons. They're not going to be split 50-50 like they were before. In fact, you might have some intuition that tells you which of the two tensions is going to be holding up more of the sign. Is it tension 1 or tension 2? Pausta. Which one is going to be supporting more than half the weight of the sign? Well, there you have a prediction. All right, we'll see as we work through the math. I now have two equations, two unknowns. I can solve them by graphing, by substitution, by taking the inverse Gaussian matrix, by converting them to polar coordinates, by typing it in to Google and asking it to solve it. I'm going to solve by substitution. Wherever I see a T1, I'm going to replace it with a T2 tangent 30 degrees. Why, there's a T1. So I'm going to write this as T2 tangent of 30 degrees times the sine of 30 degrees plus T2 times the cosine of 30 degrees adds up to 98 newtons. By the distributive property, I can pull out a T2, combine like terms. Well, I guess, distribute the T2 outside of parentheses. So right now, by the way, I know the sine of 30 degrees is a half. So I'm just going to write this as 1/2 tangent 30 degrees plus cosine of 30 degrees. In parentheses, all that adds up to 98 newtons. Now, if you want to look up the tangent of 30 degrees, it's 1 over radical 3. The cosine of 30 degrees is radical 3 over 2. But you know what I'm going to do? I'm just going to power up my calculator and ask it, what is 0.5 tangent 30 plus, whoops, darn, TI-84 plus color addition, close parentheses, plus cosine 30. Enter. And it says 1.154700538, which means 1.1547 T2 equals 98 newtons. Now, 98 divided by that means T2 is 84.9 newtons. That's the tension of the right rope. Tension of the left rope, T1, will be T2 times the tangent of 30 degrees. So if I multiply this by the tangent of 30 degrees, I get, oh my goodness, 49 newtons. Interesting. So here's a situation where the math is more involved. I had to set up two equations, two unknowns. One equation was strictly solving for equilibrium in the x direction, making them all add up to 0. The other equation came from equilibrium in the y direction, making them all add up to 0. See, this gives me a what do you call it? A linear system of equations. Two equations, two unknowns. Use your math skills and solve by substitution, elimination, whatever technique appeals to you the most. Now, should we not check this to make sure that we did it correctly? After all, these two together don't really appear to be holding up the sign very well. It says tension 2 is greater than tension 1. Well, let's do a check mathematically. For tension 1, we're saying that it is a 60-degree angle here, and that tension 1 was 49 newtons. So I would expect the horizontal component to be tension 1 cosine of 60 degrees. And I feel like putting that into my calculator. 49 cosine 60 degrees is 24.5 newtons. 49 sine of 60 degrees should be half of that, or whatever. 49 sine of 60 degrees is 42.4 newtons. Pulling it to the left. For tension 2, we're saying the hypotenuse is 84.9 newtons. The horizontal component would be 84.9 times the sine of 30 degrees, or half of that. And I get 42.5 newtons, pulling it to the right. The vertical component would be 84.9 times the cosine of 30 degrees. And I get 73.5 newtons, pulling it up. Now, does that make sense? 42.4 newtons to the left, 42.5 newtons to the right. Within round-off errors, they do indeed cancel each other out because this 84.9 was rounded. 24.5 newtons up plus 73.5 newtons up. Well, 24.5 plus 73.5, sure enough, adds up to 98 newtons up. So between these two cords, ropes, chains, they are indeed doing the job they're supposed to do of holding up the sign. Tension 2 is doing a lot more effort than tension 1 in this situation. More of the sign is being held by the right rope relative to the left rope. All right, you want one more like this? Oh, it's just physics, children. What about I have a ceiling. I have a wall. I have a stop sign, and I don't want it to fall. I have a rope going down and another one going up. Oh my goodness. And the stop sign, of course, is or traffic light isn't allowed to move. This is an equilibrium problem. So what is tension one? What is tension two? If this angle is below the horizontal, I don't know, you want to make it 30, 60, 90 triangles again? No, Costa, that would be too easy. Let's make this thing 35 degrees below the horizontal. Let's make this thing 20 degrees from the vertical. Solve for tension one, solve for tension two. Hey, that's a great question. Let's make the mass 10 kilograms again, just so you're kind of familiar with the math. I see you kids are going to solve this problem before I do. Oh man, our 3-minute timer just went off. You guys have a 3-minute break, and then we'll get back to this. Da 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 da. Okay, kids, 3 minutes of your lives have gone by. Use the time to do jumping jacks, dream about Tim Hortons or McDonald's or In-N-Out or your local equivalent. And I see some of you just spent 3 minutes getting fatter and fatter. Oh well. All right. I used the 3 minutes to solve the problem. I'm done. Santosh is saying, wait, I didn't do that during 3 minutes. And Simeon, why do I not see your camera turned on, child? Why? There you go. That's better. Of course, I don't know if I have the right answer. Anyone want me to like guide you through it already? Huh. Santosh, what'd you get? Well, I see Costa bobbing his head up and down, like as if he agreed with you. That's a good sign. Simeon, do you have T1? Yeah. Hmm. Just physics, children. Liliana, did I miss a deadline? Or have I not yet missed a deadline? For you? No. Did I miss the deadline you gave me? When's the deadline for me? Yikes. Okay, well, keep me on it because I need to be kept on it. Okay, thank you. Santosh, Simeon, T1. What do you get? Oh man. Anyone agree with that? Well, Day1 and Brendan are both giving North American indicators that they disagree with you. So Day1, what'd you get? No units? Maybe. Okay, guess what? I can physically render your grade accordingly. Brendan, what'd you get? Well, gentlemen, I agree with Santosh. I got 58.4 newtons. Children, it's just physics. So in this problem, T1 is pulling with the weight downward. It's not helping pull up the traffic sign, it's pulling it down. So T2 has to do even more work in holding up the sign. So T2 worked out to be 140 newtons, 139.99, whatever, rounded up. T1, I got, like Santosh, 58.4 newtons as this hypotenuse going downward. And what did I scribble down? I wrote horizontally, the pull of T1 to the left has to cancel the pull of T2 to the right. So T1 cosine 35 degrees, I set that equal to T2 sine of 20 degrees. Technically, one is to the left, the other's to the right, one is positive, one is negative, but they add up to 0, but you guys do the math. Vertically, T1 sine 35 degrees is pulling down. Add that to the weight of the stop sign, 98 newtons, or traffic light, and that they have to be canceled by the vertical component of T2 pulling up, so T2 cosine 20 degrees. Here are my two equations, two unknowns. I choose to substitute for T1, and I used a calculator, right? So the sine of 20 degrees divided by the cosine of 35 degrees, and that was 0.4175. Multiply that by the sine of 35 degrees here, then add 98 newtons, so 0.23949. T2 plus 98 is equal to 0.93969. T2. Math 1, solve for T2. I think Santosh got it correct. Of course, if Lisa's applauding, then that means it might be wrong. Okay, so that is section 1 of chapter 6. We're not even done doing problem example 1 yet. So let's talk about example 1. I have an object, maybe it's a tire ring, like this. And Liesel is pulling on it with force 1. Whoops, force 1. Liesel's pulling on this thing, and north is this way, and she's pulling on it with an angle of, let's make it 32 degrees north of east, and she's pulling on it with 120 newtons of pull. So that's Liesel. And then, Costa is pulling on it off in some crazy angle like this. And what the heck is this? This is an angle of 15 degrees north of west, and he's pulling on it with a force of 130 newtons. And then finally, day 1 is pulling on it with force F3. And I ask you, so what is the magnitude and the direction of F3 such that all of these add up to 0? So I sketched it as if it were going south, but it's not going to be exactly south. So F1 plus F2 plus F3 add up to 0, and that's equilibrium. So I'm looking down from above, where north is towards the top of the page and east is to the right. So this is a compass circle. Force 1 is at an angle of 32 degrees north of east. So this angle here is 32 degrees. That direction is east. F2 is 15 degrees north of west. So this little angle here is 15 degrees. What is the direction and the magnitude of F3? Okay, so you guys look like you're already solving the problem. I will point out that you have to resolve each vector into its east-west, call that the x-axis, and north-south, call that the y-axis components. Yeah, okay. So for example, in terms of east-west, First, I chose to solve for east-west first. The east component of F1, subtract from that the west component of F2, when you add the east-west component of F3, they have to add up to 0. So I have F3 pulling to the east. Okay, for north-south, the north component of F1 plus the north component of F2 are canceled by the south component of F3. So I got 97.2 newtons for the south component. Now, if I do one last sketch, F3 has a south component of 97.2 newtons and an east component of 23.8 newtons. They form two legs of a right triangle. I would use Pythagorean's theorem to get the hypotenuse. I get 100. Wow. 0.0, well, 0.1. 100 newtons. Well, 3 sig figs, 100 newtons. Now, the angle would also be required. If I take the inverse tangent of 23.8 over 97.2, I have this angle here is 13.8 degrees east of south. You could also take the complement and call that 76.2 degrees south of east. Correct me if I'm wrong. Okay, anyone spot mistakes from me? All right. Within our textbook, chapter 6, section 1, this is the idea of example 1, equilibrium physics problems, where you break them up into their perpendicular components, and individually, every dimension gives you an equation. 2 dimensions, 2 independent equations. With the system of equations, you substitute or eliminate to solve for one unknown. And once you have one unknown, you substitute back in to solve for the other unknown. All right, let's see, example 2. They have a car being towed up a hill, and they say the car weighs, oh, let's make up new numbers. This car has a weight of 20,000 newtons, which is like a pretty hefty car. And it's being towed at an angle of, let's make it 25 degrees. And it's being towed at a, by the way, there is a physics problem where the rope makes an angle with the incline, but for this problem, I'm trying to have the rope being parallel to the incline. Let's not make it too hard for you the first time. And it says friction is negligible, and the tow rope can only handle a maximum of, let's say, 6,000 newtons. And the question is, will the rope hold or will the rope break? And by the way, this is going at a constant velocity. Constant velocity. Under these conditions, would the rope hold or would the rope break? So you do a free body diagram. The force of gravity acts vertically down towards the center of the earth. The normal force is perpendicular to the solid surface of contact. The component of the force of gravity that is parallel to the incline is what we're interested in. The component of the weight that is parallel to the incline. The incline is this same angle here on this right triangle. So this angle here is 25 degrees on a right triangle. I want the opposite side. The weight is already calculated from the mass. The weight is 20,000 newtons. The question is, what is the magnitude of the component of the weight parallel to the incline? Well, that's the opposite side of this right triangle. So if I go 20,000 times the sine of 25 degrees, beep, 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 calculator says 8,450 newtons. 8,450 newtons. The tow rope, to maintain constant speed, would have to have an upward tension canceling that out, 8,450 newtons. The tow rope can only handle 6,000 newtons. It breaks, the car crashes into the ocean, your family dies. Or you could be like that Polish family where the guy lost his car keys and his family was locked in the car, and it took him a week to get him out. That's an old joke from back when people picked on Polish people. Oh well. I don't know if you guys do like those types of jokes anymore. We're heading into a world where we don't. That's a good thing. All right, so there's example 2 from chapter 1, section 1. Section 6.2. Using Newton's second law. So basically now we are just combining the kinematic equations of motion with Newton's second law. In fact, I could tell you this. Look, suppose this car was initially given a push to help it get going up the hill. So its initial velocity let's say, is 20.0 meters per second up the hill. As we've just calculated, as soon as we stop pushing it, that rope is going to break. And so my question is, from the point where the rope breaks, how far up the hill will the car coast before it stops? Okay, what is the distance delta x along the length of the hill that the car will coast to a stop? And you say, oh, well, I need to know the acceleration of the car. For the acceleration, it's Newton's second law, F equals ma. The F would be the component of the weight parallel to the incline. The M would be 20,000 newtons divided by G. I get 2,041 kilograms. So there's my M. Here's my F. F equals ma. So 8,450 divided by 2,041, I have an acceleration of 4.14 meters per second squared down, negative, slowing it down. Now life is easy. I have an acceleration. I have an initial velocity of 20 meters per second. I have a final velocity of 0 meters per second, and I want to figure out how far does it coast. This is an old kinematic problem in one dimension. I have displacement, initial velocity, final velocity, acceleration. I select equation 4. I solve for delta x. Almost doing your head now, huh? 20 squared divided by 8.18. And it says it will coast 48.9 meters up that hill. So what I'm demonstrating right now is combining the free body diagrams, Newton's second law, with the kinematic equations of motion. Three minutes of class time. They do have one more example in this section. Launching a rocket. They give you the mass, they give you the thrust, they give you the time, and they ask you what is the maximum altitude that it reaches. I don't think we could do that in 2 minutes. What do you think, Santosh? Do it or not? Santosh says, no, I'd rather just discover it during homework. All right. I think you students could do it. Anyways, the example is ignore air resistance. It's a two-step, one-dimensional physics problem. The first step, solve for the acceleration. The second step, free fall. All right, I'm not going to start anything new. We're down to a couple of minutes. I'm going to stop recording.